Continue with our morning session. It's an immense pleasure to introduce Bernd Siebert from the University of Texas, who's going to tell us about logarithmic Hilbert.
Okay, thank you, Ludmil. Thanks for the invitation to come here and give a talk. And thanks to everybody for sticking around. It's a Saturday. We should do something with the family, but now we're here. Hopefully, I can tell you something interesting. So this is a project I've been spending a lot of time on the last maybe 4 years or so. And it's joint work with Mattia Talpo and Richard Thomas in progress. There's no paper out yet. And it's built on a question, tries to answer a question that has annoyed or vexed people working in logarithmic geometry for a long time. Namely, we know what logarithmic maps are and so on, but we don't really have a good way to connect the log structure to coherent sheaves. Okay, so log geometry tells you with a technique, it tells you how to deal with relative situations, relative divisor. Like these are these two basic cases. Say you have a normal crossings divisor, and log geometry gives you a robust technique to work with these things. And then if you have a normal crossing degeneration, that's of course a special case of the first case, but then you can also look up just the central fiber and do it with a log structure and see a lot of things for the family. And more generally, you talk about toroidal or log-smooth cases. And so, of course, you can talk about coherent sheaves on your scheme, but they don't talk to the log structure. Yeah, and they should, right? So if you talk about maps between logs, let's say stable maps, you endow a log structure, and that's the first step in kind of knowing how they smooth as a topological abstraction. The same thing should hold for coherent sheaves. And why would one be interested, or why was I interested in this already maybe 10 years ago or even longer? You would like to do something like logarithmic Donaldson-Thomas or Condon-Thomas invariants for the pairs or the central fibers of toric degenerations that come up in my long-term project program with Mark. So that would be interesting for writing down Gluing formula and computations of these things in these toric degenerations or in other situations. Sometimes you're also just interested in moduli spaces of sheaves. Let's say very, very classical subjects, something like, I don't know, moduli spaces of vector bundles on Riemann surfaces. It's a paper by Giesecke who did an induced degeneration when you degenerate your Riemann surface into a normal curve, and what kind of vector bundles you could see there. Actually, that's a precursor to some of the ideas I will explain. A special case of such things is there's a family of hyperkähler manifolds obtained as endpoint Hilbert schemes of endpoints on a K3 surface.
You want to say that you consider the resolution? That's why you said that it is there? Or?
Sorry, say it again.
Do a resolution?
No, I mean, as long as the K3, yeah, so as long as the K3 is smooth, no problem, right? But then you degenerate, have a semi-stable degeneration, would like to have an induced degeneration of your hyperkähler. Okay, and if you just take Hilb end of the central fiber, you get all kind of junk. Okay, that's obviously not what you want. Maybe you want to go the other way around and say, I'm interested in constructing vector bundles on a Calabi-Yau of high dimension, and that is not, there are limited techniques to do that. It might be easier to construct it on your central fiber, which might be something like a union of toric varieties, and then you try to deform, but you should also endow the stuff on X0 with some box structure, otherwise, good luck with it. And then there's this thing with stability conditions, where people have started talking about families of stability conditions, and there's still the problem. It's hard to construct even one, right? We know whether this is infinitesimally, but might be interesting. I don't know if it works, but understanding, maybe constructing stability conditions near such a maximal degeneration. So that's, I think, a ton of motivation to think about coherent sheaves in log geometry. There are a bunch of candidates I'm aware of, and maybe there's even one more that I'm not ready to talk about. Maybe the first one is parabolic sheets, invented by Born and Vistoli, and with some final executive work by Talpo, Vistoli, 2010, where you look at, so a log scheme has an associated infinite root stack. I'm not going to explain how to get that, but there's a stack, an infinite root stack associated, naturally associated to it. And you can look at coherent sheets on this stuff. Okay, and these are essentially the parabolic sheets. And they went a certain way to do this. And actually, when I started, that's why Mattia is in the project in the first place. When I started thinking about this, I thought maybe that's the way. That's the only idea I have at the moment. Let's try. Then there is the shortly afterwards is maybe even it was before. I'm not so sure. Maybe it was on the archive before 2000. I'm not sure which one was earlier, but around the same time, completely independent development by Univ, the student was Wu. Sure, I'm pronouncing it wrong. How is he pronounced? Melissa? Okay, so maybe close. So they expanded this technique that Johnny had developed with in logarithmic theory, in logarithmic theory with relative logarithmic invariance expanded degenerations, to look at sheaves at the case where you look at this relative situation of a smooth space with a smooth divisor. And then you look at sheaves that are transverse to the divisor. If they start falling into it, you blow up in a one primitive family, you get an accordion of P1 bundles over this D and insist in keeping it transverse. And that works very well. And you can do something like some of the things I talked about before in this context. And then while we were already working on this along a different approach that I'm going to explain about, explain, not complain about it, explain, I will also complain, but because it didn't work. There was Davish Malik and Ranganathan put out a paper in 2020 where they used this expanded degeneration point of view that Drew had already generalized to normal crossing situations, so where D is not smooth but normal crossings, to do logarithmic Dawson-Thomas theory. So one-dimensional support, sheets with one-dimensional support in three-dimensional spaces. Actually, the dimension doesn't matter, but it should be one-dimensional support. So it kind of defeated our initial project, but we thought we were on something slightly different. So one feature of this that I will explain or try to explain is there's actually not just one moduli space. Whenever you talk about expanded degenerations, there's some kind of non-uniqueness. So you have to take basically what you do is you take a huge stack built from all expansions that are kind of sufficiently fine. Okay, so you fix something that tells you have to refine a certain given candidate, and then you look at transverse sheaves and you figure out, okay, they cover all the kind of equivalence class. The whole thing is compact. But if you change your subdivision, these moduli spaces actually may increase, not dimension, but they can produce some parts that are fiber bundles over the previous space. So it's not unique. So then we were following for maybe 2 years or 3 years an approach that looked very promising. So first time we talked about it, we looked at a proposal that I think many people had, and I think I also had in discussions with Paul Zosner, maybe 2000, I don't know what it was, 2015 or so. Namely, a log structure comes with a sheaf of monoids MX that contains OX star. Sir, so say it again.
That is pronounced.
He never told me. Okay, so it's not okay. But he's German, so maybe
He's Ukrainian.
Oh, okay. Oh,
Yes.
even worse. Yeah, that's right. Actually, he's Ukrainian. Okay, so and then you can build a sheaf of rings, certainly OX MX, but you have this OX star in there in both styles. So you factor out the OX star in a kind of a diagonal fashion to get something like a log structure sheaf. That sounded very tempting to try. And we tried very hard. And I will show you that why we gave up. Okay. So it's tempting, but it just doesn't seem to work. But doing this, we kind of got pushed a little bit into the expanded degeneration direction. However, in a more canonical fashion. And that's what I'm going to talk about today. So just a week ago, we found a paper by a student of Dhruv Ranganathan, Patrick Kennedy Hunt, who does something very, very similar. So his work kind of generalizes this Maulik Ranganathan point of view to all dimensions. So it's again non-canonical, but many of the problems we were still thinking about and trying to write up are already contained in this paper. So we're now kind of in contact with him to see what we can import from his paper and what else we are still writing up. But he has the same, so essentially that would say we take sheaves on what we call closed log subschemes. Okay, and closed log subschemes are not exactly what you might expect they are. Okay. Also, we never cared about the quad scheme so much, thinking that this is a straightforward generalization. So let's just talk about the Hilbert scheme, and I'll just restrict to that case. And you should think of that the quad scheme as an easy generalization. Okay, so my impression is, or my expectation is, that very few here in the room are actually actively working with log geometry. I'm not going to explain what I've done 1,000 times in my career, like what a log structure is using monoid sheaves. But maybe it's useful to think of log structures to give you a stacky perspective on log structures. It must be more palatable to some of you. That works as follows. So if you have a rational polyhedral cone, as in toric geometry, you can produce a toric variety, F and toric variety, by taking the dual at the integral points. The corresponding monoid ring, the spectrum is an F and toric variety that has a torus action on it, and you can take the stacky quotient. Okay. So, for example, in my mind, that's a bit of a funky space. But people who've grown up with stacks might find this extremely natural. So if you take A2 mod GM squared, what you see is there's one big stratum, the open stratum, the torus, that just gives one point. That looks like an ordinary, right? It's a spec K, but this point is actually open in your stack. Okay, it's a generic kind of thing. And then you have the origin that just fixed, and you have a GM squared action on it trivially, so that gives a BGM squared. Okay, and that's a close point in the stack. And then you have these two kind of mixed strata that correspond to the coordinate axis. So you have like four points in the stack, and they're related by certain closures. Okay, and then you can define a log structure locally, and that would actually, if you just take this stack here, A2 mod GM squared, and look at a map from X to this stack. So let me maybe say this here, just parenthetically. What would that mean? That essentially gives you the structure of two divisors. You know, so you can pull back these two strata that you have, these 2 points, or the closures of these rather. And that gives you two divisors with line bundles because you have the BGMs in there. And these are the normal bundles, or rather, is it a normal? Yes, it's a normal bundle. And conversely, if you have a pair X, D, D has two components, normal crossing, you will get such a map. Okay, and that's well defined. And that would be one case of a log structure. So in general, you can define log structures by taking a co-limit of such these stacks here, these kind of toric stacks, toric audio stacks. Whenever you have a map of cones, a face map of cones, you get a corresponding open embedding of a sigmas, and then you take the co-limit of this guy, and that's the point of view introduced by Martin Olsen, and you can just say this is a log structure. Okay, you have a morphism from X, from your scheme or stack or whatever to this stack, and then you get strata on X just by pulling back strata that you naturally see here, right? These are the closures of these things, or just these points. They're also strata. Pull back to locally closed subschemes of X. They're strata, and each stratum is decorated by a column. And then there's also an easy way from this point of view to say what the tropicalization of this log scheme is. Namely, you take the co-limit of all these cones that appear in your strata. I'm lying slightly, you also take, but it also takes the faces or something. But on a good approximation, this is the tropicalization of the cone complex. So if you start with the toric variety, take the obvious maps to these affine pieces, then what you get will be the fan. Okay, the fan of the toric variety is its tropicalization of the associated tropical variety. So, and then just as wrapping up this discussion on log structures, here are a few examples. So log points are just then morphisms from spec K to a sigma. Typically, you would want to map to this closed point, which was the BGM squared on the previous slide, right? So they are interesting log structures and points. And then if you have a simple normal crossings divisor, I discussed the case R equal 2, just in this parenthetical remark on the previous slide. You would that would be given locally by a morphism from an open ETL neighborhood, maybe. Actually, you don't need to type simple normal crossings. That could be an open neighborhood. To AR, and then you get the induced map to this quotient stack, and that's the local morphism that you get to define your log structure here. Okay, of course, that also works if that pair is only toroidal. Then you can also easily say what the pullback log structure is, namely, if you have a log structure on X and the map from Y to X, you just compose. Okay, so in particular, on a central fiber of a degeneration, of a normal crossings degeneration, you get a log structure. And it will just tell you what these maps to these stacks are locally. Now, one reason I'm discussing this, I want to explain to you what a log modification is. So a log modification is a morphism between two log schemes or log spaces. We need this for stacks also. And then locally in Y, okay? Locally, maybe I should write in Y, yeah? You have a chart here to a sigma, okay? This is a local thing. And then you take a subdivision capital sigma of this cone sigma. Okay, we all know that gives you a toric birational morphism from something typically not affine, toric variety of associated sigma to this affine toric variety. Okay, so that gives a map. You get a corresponding kind of stack up here, glued from all these toric pieces you have, the toric stacky pieces, and a morphism, right? And you want this guy to be Cartesian. Okay, so that means a log modification. Actually, to agree with the notation later on, maybe let me change this slightly. So you should think of this as, and then it's local in X. Okay, so that will give kind of an intrinsic way to talk about blow-ups or more general log modifications of a log scheme that might not see this ambient space. Okay, this can be very strange. So you could do a log modification of a log point and get something higher dimensional, right? So down here, this might be 0-dimensional, and that but you have a log structure of rank n in the sigma, and then this is n-dimensional. Okay, so this is a kind of strange thing. Okay, so then I wanted to tell you or complain about this log structure sheet thing just briefly. So just so it is a bit in the public domain, and nobody else will try or ask me why it didn't work so well. Maybe they're smarter than us, but so why did it not work? So that was a tempting approach to look at these sheaves, ideal sheaves now in the thing. But once you start thinking about it, you notice this OX log is just a ton of ideal sheaves. Okay, so it has to do with the fact that essentially the logarithmic information you're interested in is really the leading coefficient. But you have a bunch of other coefficients in these polynomials in here, yeah. So and that just doesn't work. But fiddling with the definition, so we can't use all ideals. We can restrict the class of ideals we're looking at, and indeed we managed to prove that pointwise we get what we want. Okay, so pointwise in X, you can show that there's a class of kind of ideals in here such that they correspond to transverse subschemes on toric blowing ups of your space or log modifications. Okay, so something like this diagram. But we could never make it work to have good generalization properties. We have no global theory. But that kind of thing pushed us to thinking about expanded degenerations a little more. Yeah, so it gave a hint that there is something maybe more intrinsic, maybe more well-defined in talking about these transverse subschemes, because that blow up would not be determined by the thing, right? It's just saying there's something sufficiently defined and look like this. Okay, so then let's talk about log Hilbert's scheme. The first notion is what are the objects in the thing? What does it parameterize? It should parameterize closed log subschemes. Okay, so before explaining what this is, so let's just take a target X, not relative, just absolute. Think of a simple normal crossings relative situation, X comma D, let's say, and you have to define what a closed log embedding is. So that's obviously a morphism. Actually, we already say what yeah, so this is one fundamental difference to closed subscheme, closed embeddings. People like say immersions, I prefer embeddings. Closed embeddings in algebraic geometry, because there you never have a base. Yeah, you don't need a base. It's an absolute notion. In log geometry, because we have these interesting log points, you already got to get a different theory and different objects. So saying, so it's a relative situation right away. Yeah, so you would start with S that could be a left point, but it could also be high dimensional, and takes a product. And then you say, you look at log morphisms, so diagrams of this form, and you impose two conditions. First is that this projection is log flat. So if this is just spec K without log structure, that's nothing, no condition. But if it has a log structure, this is a non-trivial condition. And then the crucial thing is we want that F factors, this map factors over a strict closed embedding to some log modification up here. Yeah, so we take a log modification, just think of an expanded degeneration, and then saying it's a strict closed embedding is a form of transversality. Okay, so you just inherit the log structure. Well, I should say the transversality comes from combining this strict log structure with the log flatness. Okay. So here just reminded you what log modification is. Locally given by a blow up of your chart on XS. Okay, so I think this definition, I mean, you are not log geometers typically. So probably this slide freaks you out a little bit. So let's slow down and let's give you a sense of what log flatness is, and then how it works in examples. So log flatness has a long history. It goes back to early papers by Kato, and of course Olsen also did it. It's a long unpublished paper by Gillum, treatment in August's book, and from a very different perspective, non-logging, more traditionally, Genetilev had this notion of toric transversality that is a special case of log flatness. So over log point, you say it looks as follows. Okay, so there's a local notion, of course. So locally, let's say we have a log point here. I didn't introduce that notation, but this is the log point that maps spec K to the close point of AQ. Okay, and then here you have some morphism given by a morphism, a toric morphism. Okay, AP to AQ, and you say this is. And then you have a commutative diagram like this, okay? And you say that this morphism is log flat if when you let your torus act on your embedding, so sorry, not embedding, on this morphism, yeah, so this is, the relative torus. So that's the relative torus for this toric morphism. It acts on the fibers of this toric morphism, okay? That is this guy. And you act on it, and you look at the induced map to this fiber over the origin. Okay, Z lies over the origin, so it doesn't make sense to say look at the torus action and see what happens for this map. And you want this map to be flat. Okay, so let's do some more concrete examples. Let's say Q0. So you're talking just about some subscheme of a toric variety, and you ask when is it log flat. That's Tevelev. So the definition is you just look at when the map, the torus action defines a flat map to your torus, to your toric variety. So log flatness means toric transversality. Then the Wu-Li paper is a special case of the log structure for the smooth divisor. So in this case, you take P equals N, Q equals 0, and then log flatness relative to this divisor means a vanishing of this tor. So this means that there are no kind of embedded components of Z inside D. Yeah. So then here, let me highlight, maybe I should add actually a slide here. Let me just for what is C. So C, I think I should draw a little cartoon here. So I'm taking A2 and look at the map that just maps that thing to the diagonal. Okay. And then you ask, so now there's one special point, you have to logarithmically, there's one special point, but there are two obvious log structures you could put here. The one is that makes A1 a toric variety. So this would be the first, sorry, that's the second case. So maybe this is 2. Here, so this is 2, this is 1. So for 2, you take at this point an N. For 1, you take the strict transform, so you take the pullback log structure. So if this is you take the pullback, so maybe this is the Yoda upper star and A2, and in this case you would put an N squared at this point. Okay, so both are log maps, The second one is log flat. The first one is not. So why is this related to our definition of closed log subschemes? If you pull this down, the second case factors over a blow up, and it's a strict closed embedding of the thing. Yeah, so if you take this inclusion in the blow up and takes the induced log structure, you would inherit an n, not an n squared. Okay, so that's a strict closed embedding. The factorization is log flat, okay, over the trivial log point spec k. And so that second morphism, this one, the inclusion of this line, this guy is actually a closed log embedding. The first one is not. Okay, so the second one kind of remembers that you should think of this as living on some blow-up. Other questions? Is the picture roughly clear? So the point is now we have a class of morphisms between log schemes, and the good ones are the ones that factor over induced log structures pulled back from a log modification. Okay, so that's closed log embeddings. So, but then the interesting thing happens. So if you think carefully about what a closed subscheme is in algebraic geometry, it's an equivalence class. Okay, it's an equivalence class of closed immersions or closed embeddings, and you identify two if they fit into a diagram like this, a congruent diagram like this. So here in log geometry, the difference is you don't only want to consider isomorphisms, but what I call log étal morphisms, and these are just log modifications. I mean, not only log étal, you want log étal might be too small, but you want log modifications of the target. So you want to identify two morphisms, two closed log embeddings, z to x and z twiddle to x, if they are related Dirichlet. Yeah, so this is the other one. You want to identify z and z twiddle if they just pull back to the same thing after a log modification of the target. Okay, so in this factorization in the definition, I now allow here this factorization. I now allow different kind of targets, but if I want to lift it to a different different log modification, I would use this kind of pullback in what is called the FS log category, which is something like the strict transform. Okay, so this is this FS Cartesian. I'm sure virtually nobody in this room is really familiar with this theory. So there's a notion of kind of strict transform mechanisms. Okay, so and then we indeed get a stack. Well, it won't be algebraic. Okay. Actually, I thought it was algebraic until about a week ago when I thought more deeply. I never thought very deeply about the stack of all things. Okay, so this is like the thing you have in log monothetan theory, where you just take all stable log maps, and that's just not useful. Okay, so this is not finite type. It's not separated. It's just looking at too many things. Okay. But what you can observe is, so in Patrick's work, that has a little more meaning, and he works with it, and I don't think he proves that it's not algebraic, but it's rather clear that it's not algebraic. It contains something like the co-limit of all toric varieties of the same dimension. F1 toric, something like this. So you take an F1 toric variety, you subdivide, take all of them. Takes a co-limit. I don't think that's algebraic. Okay, so but it has covered by open substacks that are algebraic. And how do you get these? Well, fix one, explain the degeneration, and take the relative Hilbert scheme of that guy and divide out possible automorphisms that you might have. Why would you have automorphisms? Well, if you just blow up like the relative situation, of course you don't. It's a birational morphism, right? But think of an expanded degeneration. So you have this P1 bundle over D, and of course that has a GM match. So plus you also have this. It's a whole. Actually, that is not the thing I'm talking about. It's you want the automorphism on the base that interact with it. So anyway, so you can write down an open subscheme of a relative Hilbert scheme, divide out an automorphism group, and that are these algebraic subsets. Okay, so it's not separated. It's far from finite type, even after you fix over polynomial, and that is common in log moduli problems, like for stable log maps, because you can just always pull back by morphism, let's say of log points, right? You have something over spec K, you just pull it back to a bigger log point, to something that has a higher monoid, bigger monoid, right? So you can always put on some factors of n to L, for example. So it's just not finite type. In addition, these kind of things are not algebraic, right? This is what I was saying about this. Another reason why this thing is not only not of finite type, but it's not even algebraic. Okay, because you have these kind of crazy colimits in here. So so essentially now I come to the main point of the lecture. I will not talk about the many things that you have to check in proving that this is a good theory. But I will tell you the main idea why we believe that we have a canonical log Hilbert stack rather than just the thing that Doof and Davish produced and Patrick also produced, that depends on a choice of a subdivision. So maybe okay. So let me first tell you what naively you might have in mind, okay, and where I'm coming from. If you take a tropical hypersurface in a cone, okay, so you tropicalize a hypersurface in an F-toric variety or something like that, you end up with this situation. And you find that one of the basic results in tropical geometry, that this gamma, this tropicalization, is a support of a balanced rational polyhedral complex. Okay, so these things that you call tropical varieties. And then there's a task to parameterize all the gamma that appear by a polyhedral complex. Okay, and for hypersurfaces, I think everybody in this room knows how to do this. You do this by the secondary polytope. Okay, so you wiggle with your coefficients or the secondary fan, and you get all the variations. Okay, neatly arranged into cone-like structures. So let's do this for a very simple example. Let's take this hypersurface xy plus t to ax plus t to by plus t to c. Okay, depending on what these what the powers are, a, b, c. So the degenerate case is if a plus b is c, then you just get this kind of tropicalization. Sorry, this is tropicalization. This is the kind of polyhedral decomposition of the momentum polytopes that you get. So you have the monomials sitting here. This is the monomial for x, monomial power t to ax. So that puts an a here. That's a y. Here's the xy, and here's a constant. And then wiggling with these powers just means you look at the corresponding subdivision. So that would give this subdivision. Dually, you obtain this thing. If a plus b is less than c, so you lift that point c, you get this kink here, and the corresponding dual subdivisions are like this. But wiggling with a, b, or c just tells you get different tropicalizations, and you get all the tropical model line. And if a plus b is larger than c, so taking c down, you get this freeze and correspondingly the tropical objects, tropical curves look like this, but you still have three parameters. So the tropical modular space consists of two three-dimensional cones, both simplicial, ABC, and they have one joint face, a facet, which is this one. Okay, so you would like to do something similar in higher dimensions. And now comes the kind of very disappointing thing. So let me first say this thing here. And yep, go ahead. It's just all the monomials. I'm just well, if you think of the ignore it if you want, okay? I just think of the whole thing as taking the graph of the function of coefficients, okay? And if you take that and extend it, so if you want to build this polytope, think of the Newton polyhedron, okay? So the Newton polyhedron will be, it's a local case. Maybe that's confusing you. It's a local case. It's not a projective case. So I'm working in the ring Kx1, X and Y. So you're doing a Newton polyhedron of three-dimensional Newton polyhedron of a singularity, and they are unbounded. Maybe not so important. We can discuss a few later, but I just wanted to tell you why I want this cone-like thing. Okay, so then you start thinking about higher codimensions and mixed dimensions, and you immediately run into trouble. Okay, so all these good moduli problems, or coming from, let's say, logarithmic theory, or curves, nodal curves, you have to define a notion of tropical varieties that are of the same type. Okay, so the ones that you want to put in one family, that are parameterized by one cone of the tropical moduli space. Yeah, so that's a basic thing. You want to say these. So like here, right? We have three types. Yeah, so these are the three types we have. You put these in everything that looks like this, which has this kind of edge, you put in one family. This is a boundary of that guy, is another type, and here's still another type. So that's the thing you want to define. And then whenever you have two tropical subspaces of the same type, define an addition. Okay, that will give you a cone structure. Now let's look at 2 points in A2. Okay, or actually it's a point. It's a log point with n squared. Now you can rotate these points and change position, right? You can just swap and go around. And obviously that is not possible to be parameterized by cone, which is something convex. So not all of these things where they don't meet can be one type. But how do we distinguish? I mean, how can they not be one type? I mean, at what point, why is there anything special in here? And something similar, which also comes up when you tropicalize two skew lines in A3 and take a limit, degenerating to two coordinate axes, you get these kind of things. So two skew lines in R3, or half rays actually, and one is on top of the other, and then there's a special position, they go on top. So it looks like you should somehow single out some point here, because when they meet, there should be some point, right? So that doesn't look like it would be a boundary point of a cone. And even worse, if you think of, and that is actually at the heart of why expanded degenerations don't give you something canonical, there is an example of Sturmfels and Tevelev. The implicitization paper. They produce an example of a three-dimensional. So it's a tropicalization of something. Let's put it this way. So they have a three-dimensional thing in in C star to 5. And then they tropicalize. That gives a three-dimensional tropical variety in R5. And that guy, as a subset, has two cells. Tau1, Tau2 in gamma, 2 cells. They're actually triangles. I think they're standard triangles, I'm not sure. Let me just draw it schematically. Tau1, Tau2, and they intersect in one interior point. So that doesn't look like it's, so if you think about it, there's just no distinguished polyhedral decomposition of this thing. Yeah, so it's something one might not be aware of when you sometimes see proofs of that the tropical variety is the underlying space of a polyhedral cone complex, okay, or polyhedral complex. But the cone structure, the polyhedral structure, comes from choosing a compactification. Yeah, so that's what's going on here. And depending on how you compactify the C star to 5 in, let's say, a toric variety X, will give you, I shouldn't call this X, a toric variety will give you different answers of what polyhedral decomposition you have. Okay, so that's at the reason of this, at the core of this phenomenon. Okay, so before telling you the answer that we propose, our proposal, let me remind you a little bit, or maybe give you first a glimpse of what we call basic or minimal log structures in log moduli problems. And here's an example that everybody of you is very familiar with. Let's look at the Deligne-Mumford stack of nodal curves, MG, stable curves. And MG has this divisor in there of nodal curves. Okay, that's a normal crossing divisor. It has stacking, whole thing as a stack, but as a smooth stacking way is a normal crossing divisor. And the local structure is just given as follows. Let's say we have a 2 nodal curve here at this point, and you look at the versal deformation of this guy. There might be some smooth factors, but up to smooth factors, there's these 2 parameters, smoothing parameters of the nodes. And these gives you the 2 components of this DG. Okay, so this component would keep that node, but smoothes that one. Okay, so this kind of direction is the smoothing parameter of that node. And conversely, symmetrically, you get the smoothing parameter of the other node. Okay, so and then there's a fact that suggests you what to do in log geometry. Namely, log geometry for this thing is a tautology. Namely, you just take the log structure you get for this pair, MG, DG. It's a normal crossing divisor. We know it comes with a log structure. And that gives you a distinguished log structure, which would put down here an n, a copy of the natural numbers to the number of nodes. Yeah, so here's an n to the number of nodes. Here's a 2, okay, or L, I said L. I put it here, right? Sorry, put it here. So that just means, and then you have the fact, this is universal. This log structure is universal, that whenever you have some decorations of the correct things in log geometry that tells you have a nodal log curve, then that can be over anything, right? So you can have like 1 parameter families. S could be a standard log point where you just have 1 copy of n. But it's always given by a unique base change coming from this kind of universal thing that we produced by just taking the pair. So we call this n to L, the number of nodes, the basic monad. Okay, that is the basic monad. It is the one that kind of captures the log geometry of the situation. And example 2 one of the happiest moments in my mathematical career was that I had the insight that for stable log maps, you can produce the basic monad as the dual of the tropical moduli space. Okay, so whenever you have a diagram like this is a nodal curve with log structure or something, let's say a log point. This is your target, something you would like to define log of invariance of. It has a tropical moduli space, right? So you tropicalize this, and it gives you a length graph, or rather a family of length graphs over the tropicalization of this thing, which is maybe a cone. Okay, well, let's just work locally. Then we have a cone here, and that the tropicalization of this guy gives you a length graph. Do I have this somewhere? I don't. It's coming later in a slightly similar fashion. Okay, anyway, so you tropicalize, you get a gamma over, let's say this is a log point given by Q, then this would actually be reaction. So what I want to write is a Q dual R. So this is a dual cone, right? So home Q to R larger equals 0. And that's a family of length graphs that maps to this tropicalization of X, which is a cone complex. Okay, and you can talk about tropical moduli. That's a cone that's given as by a cone, comes with a type, and the dual of this cone is a Q. Okay, so that is a Q. Well, he takes the integral points. So here's one example of what this looks like. Let's say you take connex in P2, and some of these that have lots of contracted components. So this one is a generic component, so some kind of line in P2, but then you have other components mapping. This one maps to one of the divisors, and the other three just get contracted to a point. And you get a tropicalization that looks like this. You have three moduli, tropical moduli, oops, A, B, and C, and then you just get a basic monad at NQ. Okay, so we want to play a similar game for the log Hilbert scheme. So here comes the main point of the talk. So if you go home and you got lost on page 2, maybe you can take home the following. That the suggestion is that the problem of defining the log Hilbert scheme is intimately related to hyperplane arrangements. Okay, so how do we do this? So similar to what I told you on the previous slide for log homomorphism theory, when you have a closed log embedding, you get this kind of diagram, right? And you can tropicalize, and you get a family of tropical subspaces. That is actually honestly a cone complex, okay? Over this base space, which is there's an unfortunate clash of notation. So that's a little that's a little s, and it has nothing to do with this capital S that I had a base on the left slide. But it's also a base parameter, but a tropical base parameter. It's like dual to this thing. So over each point of this dual cone that I had on the previous slide, I get not a length graph, but some cone complex. Okay, and that has similarly a map to your tropicalization. And the problem that I alluded to before when talking about these expanded degenerations is that the polyhedral decomposition of this gamma S depends on changes under the equivalence of log embeddings, because once you do a log embedding, you may subdivide, right? Becomes a subcomplex of something, and to subdivide the image complex, you need to induce subdivision of your subspace. Okay, but still locally in X, it's this gamma is a support of a balanced polyhedral complex. Okay. Now, the tropicalizations. So one problem is that the tropicalization, the flat pieces of a tropicalization may not be convex. Okay, if they were convex, just take these, right? It's easy. But they may not be convex. So we define a notion of flats, kind of the obvious thing, right? So what are the flat pieces in a tropicalization? And then each flat piece, these can have various dimensions now. You obtain a hyperplane, actually a bunch of hyperplanes. And the basic idea is this whole thing sits in, so this is an argument that is local in X, okay? At each point of X, it belongs to a log stratum, it comes with a cone. So this thing, the F, sits your tropicalization at a point, yeah? This sits in this PR dual, which is the, so this is like the sigma for stratum, one stratum, one of the strata of X, of your target. Okay, so this sits in there. Actually, it's not X, it's the, no, sorry, it's X. Okay, so you can define a hyperplane arrangement by cranking up the dimension. And you do this, so this is the linear space, the affine space generated by this flat. And then you add on the tangent spaces of faces of this ambient of your cone, of your sigma. Okay, so you're in some quadrant, octant, whatever, there is something, and then you just extend. So that defines your hyperplane arrangement. By just doing this for all flats and all taus, you just take all the ones that produce a hyperplane. And that gives you a polyhedral decomposition. Any hyperplane arrangement gives you a polyhedral decomposition. So that's something canonical at each point of X. Let me see. So maybe I take the example first. Okay. So you have some picture in your mind. So let's take still kind of thing familiar from logarithmic written theory. You have seen this as also you have a tropical curve. But you look at it, some part, you see I had this, where was the tropicalization in, here, right? So here I have 3 maximal cones. And in each cone, you now have such a picture. These are the 3 toric fixed points of P2. So now we do this at one of the points. So this is one, gives you one kind of quadrant. And in there you have a chopped off tropical curve. Yeah, so these are the intersection of the boundary components. And now you extend these, so any of the, sorry, not this one. No, we do this one because this is also a cell. And what you get is this kind of hyperplane arrangement. Okay, just a bunch of arrays. Now, you can deform this picture slightly without changing the type in logarithmic written theory, but what you see here that is once these two kind of things align, you get a different type. Yeah, so these two things have a different type from the point of view of the log Hilbert scheme. So only 2 more slides. So the type is then defined by the hyperplane arrangements, but then to tell you what the tropical subspace is, the tropical subspace is a union of cells of your hyperplane arrangement. So you just define a certain category of fans and tell you that keep track of the cells that actually belong to this gamma. Okay, and the type is the type of the hyperplane arrangement plus this kind of subcategories that you defined. Okay, so not much content on this, many words to say one thing. That's my last slide. So then the key lemma that is already written is that tropical subspaces of the same type can be added. Okay, so you do have a cone structure. Okay, so hyperplane array. So actually, I couldn't find this anywhere in the literature. If any of you know this, please let me know. I don't know. I don't think the hyperplane arrangement community has ever defined something like type, this kind of type. What they have is all kinds of like homological type. So they would look at certain homology groups that you get, and that would be the type. But not this kind of refined type that we need to define basic monads. And the addition is compatible with generalization maps. So that is not obvious if you think about it. Because you see here, if you go to a neighboring stratum, might not be obvious from what I told you, but with a little experience, you know, it just means you intersect the whole thing with one of your boundary strata, with one of your faces. So from this point of view, you only see this one point, okay? It's just saying that if you look in your X, you vary your point X at some point, well, there's not much to see, right? It's just not, your Z doesn't intersect that point. So here's just one intersection point with the divisor. And what would be the hyperplane arrangement? Well, obviously, right, it's just this point. That's a hyperplane arrangement. But we do get more points here, right? So the hyperplane arrangement you get by generalizing is a refinement of the hyperplane arrangement you would see at this point. Still, you get this map. You get a face map for the corresponding monoliths. So and then you have to prove it's an open property. That's not so hard. Has to do with it's pretty similar. Okay, many other things. Fortunately now written out. Fortunately or not so fortunately for us, I don't know. Less work, but has been done by Patrick. Like boundedness, we're still thinking about. I think he has essentially a full proof. But maybe one upshot is, from a purely tropical perspective, you also have a problem of defining the tropical Hilbert scheme as a tropical variety. So here's a suggestion on how to do that, namely use hyperplane arrangements. Okay, so that was all I want to say. Thanks for your attention.
Thank you.
Well, what was the role of this minimal structure that you can make?
The what?
Minimal structure.
The minimal log structure.
Minimal.
Not O minimal.
Okay. Okay.
No. Okay. Just minimal. It's the same as basic. I like basic. People don't. Some other people don't like basic, and they say minimal.
Okay.
So right. So yeah. So this is maybe from a stack theoretic perspective, maybe that's an interesting aspect now that you're mentioning. Yeah. So typically you have something minimal, right? In a category or a stack. Yeah. So you want to show there's some universal thing. This thing is not universal for all families of closed log subschemes, just because you insisted you want the same type. But it's easy to write down families where you change type. So like here, right? I can immediately, if you give me a minute, but I don't take the time, I can easily write down a one parameter family that produces, it's a two parameter family that produces this kind of thing, okay? Where this point would move all the way around. So that would not be a pullback, that family, from our stack. So here I would not allow to kind of change this configuration. Slightly ugly, but that's a fact of life. Either you have something canonical or it's not algebraic.
Other question? Anyone?